All right, so we are rolling, and then right here, oh shoot. So there's gonna be a link called Class Videos, and that's where you'll go to get the link to the video. I put that up later today. Okay, and then all the videos will be listed in that area. Okay, if you go to syllabus, let's just briefly talk about the course here. Syllabus is there. Okay, so that's me again, Mark Ashbrook. You can call me Mark. Email is by far the best way to reach me. If you try me by telephone, you're just trying to catch me in the office. We never listen to the messages. Don't leave a message. Email me, okay? And then my office hours, ECA 209 is right across from the ASU bookstore, right across the street from the ASU bookstore. And office hours, Mondays 12:30 to 2, Wednesdays 11 to 12:30. And then I showed you our home base is Blackboard. Okay, so this is course description, prerequisites. Okay, so what you need for this course is just some version of the textbook, and that's it. There's some big bundle, it's overkill, and it's expensive. That's too much, so that gives you, all you need is one version of the textbook. Does anybody happen to have their textbook with you? So I can see. Yeah, so there's a loose leaf version, that's probably the cheapest, but this is the cover you're looking for. This bluish green, aqua, turquoise cover with the waves, calculus, second edition, Briggs and Cochrane. There's another version. Hold it up. There you go. All right. So and that could be a physical copy, or you can just get a subscription to My Math Lab, and then you have the ebook. But we won't be using My Math Lab for online homework. So that's would be the only reason for you to have the My Math Lab is just if you want the ebook version of the book. Okay. We're going to use WebWork for online homework, okay? WebWork. So you're going to need some kind of graphing calculator. The TI-83 most of you have, that's fine. Here's a calendar of topics and special dates. Okay, we'll have 3 exams in class on Fridays. And then the final exam, the date and time is known. Tuesday, May 2nd at 7 p.m. So form your schedules accordingly. Don't buy plane tickets for the first or the second during the day. You know when the final is, so be here for the final. I'm not going to entertain giving an early final the second week in April because, I just realized I have these travel plans. You know now, so make your travel plans so that you'll be here on the 2nd at 7 p.m. Basic stuff. You can read it over. This is all just fine print. So the key thing is that you have some copy of the text, a graphing calculator, and this is our schedule for the course. Any questions on the syllabus, which is available to you at Blackboard? Yes, please. No, all the exams are in class on Fridays, in class. So for those of you who had me last semester, we're taking exams in class on Fridays according to that schedule. Okay? Other questions? Yeah? Yeah, go to recitation today if you have recitation, or is it Wednesday? Yeah, you will have, you go to recitation today. They will take attendance. Other questions? That's a really broad question. If you have a specific question about what's different? Content? This is a difficult. Just pay attention to Blackboard. Blackboard gives you everything you need to know.
So it says that you need a graphing calculator. Will we get another thing for GC?
No, so you won't. We're not going to. Those who had me for Calc 1, if you still have access to GC, that's great. You use that. Okay, I recommend that you use that. But if and it should still be good. That you should still be able to use that. Okay. Yeah. So, but if you did not have me before, then just a handheld graphing calculator. Okay, some handheld graphing calculator. Other questions? Lots of questions. Here we go. In this class on Fridays. In the classroom on Fridays. We're going to take exams in class on Fridays according to the schedule. Other questions? Okay, let's do some math. Here we go. All right, so in Calc 1, you were exposed to something called the Fundamental Theorem of Calculus. Or you should have been. Okay? And the representative, symbolic representative of that Fundamental Theorem of Calculus is this. Okay, in Calculus 2, much of the course is about integrals. And when you look at this equation for the Fundamental Theorem of Calculus, you should identify an integral. Where's the integral? On the left, right? That's an integral. Okay, so if much of the course in Calc 2 is about integrals, all right, then we'd better know what the fundamental theorem is all about. Okay, because the fundamental theorem integral is a huge part of that, and it's a huge part of Calc 2. So we're going to take 2 days to deconstruct and build from the ground up what this thing is all about. Because my experience has been, if you did not have my Calc 1 course, you kind of learn this as something to plug numbers into and do a procedure. But this is chock full of meaning, and really important meaning, okay? And so we want to know what that is. So we're going to take 2 days to kind of build this from the ground up, okay? And this will be review for my Calc 1 students, and hopefully it's review for everybody, but my suspicion is it's not, okay? So here we go. We're making sense of this thing, which is the fundamental theorem of calculus. And so I have a series of principles we're going to work through, and so before we even get started, there's principle 0. And principle 0 is variables vary. Variables vary. That's why they're called variables, okay? So what do you think when you see this? 2x minus 7 equals 0. What do you think about x? What do you think about x? But 2x minus 7 equals 0. So what do you think about x? Does it equal 3.5? Could it be 4 or 10 or negative 0.5? Yes.
X could be anything. It's just in that instance, for the equation to be correct, it would have to be.
Did you hear what he said? So could x be 4? Yes, it could. So and that's maybe a different way of thinking that you've seen in your algebra in the past. X could be 4. It's just that when you put 4 into that equation, it doesn't make it true. There's only one x that makes it true. So this may further emphasize this point. If x was defined as the number of hours elapsed since your plane left the ground, okay, could x be 4? Sure, that'd be 4 hours since your plane left the ground. Could x be 10? Yeah, could x be negative 0.5? Some are saying no, some are saying yes. How could x be negative 0.5? No, but in this context, number of hours since the plane left the ground. What's that? Half hour before you take off, right? It'd be 30 minutes before you took off. Your plane left the ground. So all these x's are possible. And then maybe this equation has to do with the first time that you got peanuts, right? Maybe this equation helps you to figure out the first time on the flight that you got peanuts, okay? Angry passengers, right? Angry passengers. It's too many hours to have a snack, right? But so that's the idea, is that when x is a variable and it's can take on many values. It takes on a half an hour. It takes on 0.8 of an hour, 1 hour, 2 hours, 5 hours, 10 hours. It takes on all those values as this situation unfolded, right? As the situation unfolded, okay? So this could really take on any real number. Okay, so then there's this thing dx, okay? And for us, dx is also a variable. What does dx represent? What does dx represent? Robert?
Small change in X.
Okay, so dx is related to x in that it represents some change in the number of hours, okay? So if we talked about maybe, so suppose x was 3.5 hours, and then a little bit later, x was 3.62 hours. Okay, so you got your peanuts, and then you had to go to the bathroom. That was time x2. That's when you had to get up and go to the bathroom. Okay, so what is, in this situation, what is dx? Given a starting time of 3.5 hours since you took off and a finishing time of 3.62 hours since you took off, dx would be 0.12 hours. So it's this, it represents this change in time starting from when you got your peanuts to when you stood up to head to the bathroom. Okay, so it's that that duration of time, right? This change in time, 0.12 hours. Is that the only situation where there was a change in time of 0.12 hours? See, it's not 0.12 hours since the plane took off. It's a change. So there's actually there's many ways to express or to think about a change of 0.12 hours. Right? 0.4 hours to 0.52 hours since your plane took off. That would also have that same change. That same change in time would also be 0.12. So a change in a variable can start at any value of the variable, can start at any particular value of the variable. And it represents, now instead of how many hours since your plane took off, it's some change in time during that flight. Okay? Questions on that? Okay, so variables vary, and dx is a variable. So we could think about this change in time of 0.12 hours. It itself changing. Okay, it itself changing. A duration of time increasing, say from 3.5 hours since the plane took off. So 0.12, 0.15, 0.2, 0.5, 1 hour, all being a duration of time during the flight. Okay, so here we go, principle 1. Rate of change. Rate of change is the underlying principle, or a key underlying principle to the fundamental theorem. So we're gonna build this from the bottom up, real basic. You're buying trail mix. It costs $3.20 per pound. Okay? After scooping some mix into your bag, you decide you want more. What additional cost will you pay for 1.5 more pounds of trail mix? Everyone figure it out. You're writing, you're figuring it out. What additional cost will you pay for 1.5 more pounds of trail mix? Everyone's got a pencil in their hand, or you're typing. Did you hear me? People are sitting there. Pencil in your hand, or you're typing. You're figuring it out. Someone had their hand up here. Yes, sir. And how'd you get that? He said 3.2 times 1.5, and you got 4.8. So we're going to hold on to that calculation for a second. That's an extremely profound calculation. It seems super simple, right? This is like, what, 6th or 7th grade, right? But for calculus, this is extremely profound. So what we're going to do is we're going to say, I'm going to give you a set of variables. And given this context, I want you to define in words what each of these variables is. So x is what, y is what, dx is what, dy is what, and then m is what. And then you're going to decide, is the particular value of the variable known in this situation? So you're going to define them with words, all of them. And then for each one, you say, is it known? And if it's known, what is its value for this situation? Okay, a minute, go. And work with the person next to you if you want. Go. So let me give you an example. X is what? is the total number of pounds of mix in the bag. The total number of pounds in the bag. That varies, right? That can vary. That's a variable, the total number of pounds of mix in the bag. Okay, take it from there. Go. Okay, so here's just a little ground rule for the semester. Whenever I put you to work on a problem, if I don't say otherwise, eventually I want you to talk. I want you to talk to someone next to you. Ask questions, compare your work. Don't make me say that all semester. If I put you to work, you are free, and I encourage you to talk with the people around you. Okay? So, meet the person next to you, compare what you came up with. Go. Okay, here we go. Here we go. And when that's the case, when you guys are working together, the TAs will be here, and we'll be circling around myself also to get help. So first TA is Elpie. Is Elpie there? Is she there? So Elpie will be Monday, if you're in Monday recitation, she's your TA. So she'll be here to help you out. And then Ben is, if you're in Wednesday recitation, but anybody can help you during lecture. We all can help you. So if you're, get the help you need. If you're not figuring it out between you and the person next to you, then call one of us over. Okay, so what is Y? Y is the total number of pounds. X is the total number of pounds. Y is total cost of that number of pounds. Okay? So what is dx? A change in the number of pounds. Okay? dy? A change in cost. And m is? Cost per pound, constant rate of change, $3.20. Okay, so in this situation, do we know what x is? Do we know what the value of x is? The total number of pounds of mix in the bag. Yes or no? No, we don't, right? It says after scooping some, we want more, and we're going to put 1.5 more pounds in. Do we know what x is? Something greater than 1.5. X is unknown. So in this particular context, the current value of x is unknown. What about y? Same thing. If you don't know what x is, you can't know what y is. So x and y are unknown in terms of total number of pounds and total cost. dx, do we know what dx is? That's our 1.5 pounds, right? So this is an additional amount, right? We had some, and then we added more. So that the dx is 1.5. All right, what about dy? Is it known? How do we know what dy is? Change in the cost. And so it's how much more we're going to pay for 1.5 more pounds. And how much is that? That's what we did up here, right? That's what we did up here. And then the constant rate of change, cost per pound, is our known value of 3.2. Okay? So now, so back to this calculation that we did. Now I want you to rewrite that calculation, but using the variables. Using 2 or more of the variables that we just defined out of those 5. I want you to write an expression that represents this calculation that you did to find out the additional costs that you would pay. So I want an equation using 2 or more of these variables at left. Okay? So what variable did we actually solve for? What were we finding? What variable? This is asking about dy, right? This is asking about dy, right? And then how did we find it? M times dx. So this is what you did in symbolic form, right? In symbolic form, this is what you did to solve this very easy problem. You took 1.5 per pound times the change in number of pounds, and that gave you the change in the cost. Okay? This is how we think about constant rate of change. Constant rate of change. This equation embodies the way we want to understand constant rate of change, right? What does $3.20 a pound mean? What does it mean? It means that given any change in pounds, the change in cost is what? 3.2 times as much. So if the change in pounds is 10 pounds, then what do you know? If you add 10 more pounds to your cart, it's going to cost $32 more. Additional $32 more. If you add half a pound more to your bag, the change in cost will be 3.2 times that. Okay? This is a crucial underlying fact in the fundamental theorem of calculus, okay? And it's the way we think about constant rate of change. That a constant rate means that given any change in your independent variable, the change in the dependent variable is m times that change in the independent variable. Let's practice some more. Any questions? Okay, next you remove 0.4 pounds from your bag and return it to the bin when no one's looking. Okay? Define the variables with words. Figure out their values. Go. 30 seconds. Okay, what is the change in pounds? 0.4. Is that right? Negative 0.4. So when you have a change, you can have a negative change, which means a decrease in x, right? A decrease in x, and that's exactly what we have. So the change is negative 0.4. The amount of x went down, so the change will be negative. dy then is? Right, it's 3.2 times. That's what this number 3.2 tells us. It tells us given any change in pounds, that the change in cost will be 3.2 times as much as that change in pounds. It doesn't just tell us that 1 pound is $3.20. It tells us a lot more than that. It tells us how much what 2 pounds is. It tells us that 2 pounds is $6.40. It tells us that if we remove 1 pound from our bag, that our cost goes down $3.20. So what'd you get for this? Anybody? 28? Okay, so changes can be negative. It means a decrease in its associated variable. Any questions? Here we go. Soldier lowers an American flag from the top of the pole at 0.75 meters per second. How much does the height change from 0.6 to 2.4 seconds since the flag left the top of the pole? So I'm going to tell you what y is. Y is defined as the height of the flag from the ground in meters. I want you to define each variable below, state the value in the situation if it's known. So same things before. You're going to write out first phrases for all of them, complete phrases, including units, and then decide, do you know the values of each of them? Go, think, and then talk. This is the last time I'm going to remind you. Talk when you're working by yourselves. Check with the people around you. Ask questions. Okay, here we go. What is x? Okay, time is not a fully descriptive. Okay, time in seconds. Since when? So, yeah. So you have to describe what amount of time are you talking about? Okay, since the flag left the top, or since the soldiers started lowering the flag, or something. All right. So x is time is not clear as to what you're talking about. We could define 5 different time variables in this situation, or 12 if we wanted to. But we want specifically the time since the flag started coming down in seconds. Y we already talked about. That's the height of the flag in meters. Okay, so dx is some change in time in seconds. Dy, change in the height. What is m? Okay, that's our constant rate of change. Okay, so we'll start with that one. Is that value known in the situation, the constant rate of change? And it is? Okay, lots of some I hear some saying it. It's not 0.75 because of how y is defined. Y is defined as height, which is positive going up, right? But what's happening to y? Decreasing according to that convention of positive going up. So if you said negative 0.75, pat yourself on the back, right? Because you have to look at how y is oriented. Y is oriented. Positive is up. And this flag, y is decreasing. It's coming down. So the constant rate of change must be negative 0.75. Okay, do we know the value of x? Do we know the value of x in this situation? We know a couple, right? We kind of knew, right? We know a starting and a final value of x, right? So in this situation, it's kind of like x initial is 0.6. That's a value of x. And this is also a value of x. X final is 2.4. Isn't that true? And then x is going to take on every value in between those, right? So starting at 0.6 seconds, it's going to take on every value from 0.6 to 2.4 as time goes by. Okay, but we do have a couple of key values of x that we could point out, right? Starting value of x, final value of x. All right, y. Do we know the height? Y. We don't know that at all, right? So we don't know how high it starts because we don't know where it started from at 0, right? So unknown. What about dx? Do we have dx? It is? Right, so one way to get a change in a variable is just take the final value of that minus the initial, right? So if it started at 0.6 and ended at 2.4, then 2.4 minus 0.6 is going to give us that duration of time, 1.8 seconds that went by from 0.6 seconds after starting to 2.4 seconds after starting. All right? And so then what about dy? Do we know what dy is? So what does this negative 0.75 meters per second tells us? It tells us that given any change in time, the change in height is negative 0.75. What's going on? What's doing that? I don't know. Negative 0.75 times okay? This is the meaning of that number, negative 0.75. Given any change in time, if 1 minute goes by, if 1 second goes by, it tells us the change in the height. Okay? If 10 seconds goes by, it tells us the change in the height. It tells us the change in height for any number of seconds that go by. So in this case, how many seconds went by? 1.8 seconds went by, and so then we multiply by negative 0.75, and we get how far the flag came down, which is what? Negative 1, though, hold on, remember this number. I hope you're all taking notes. Negative 1.35, is that meters? Okay. Which is the change in height. It's how much in that time period of 1.8 seconds the flag came down. Questions on that? This is the key principle, and it makes meaning out of this number, negative 0.75 meters per second. Given any change in time, the change in height is negative 0.75 times that change in time. That's what that says. And that's the meaning of that constant rate, negative 0.75 meters per second. Anybody have a question? Okay, so now I'm going to show you a graph. Over here on the left, there's a graph. That blue line there, that blue line. I want you to make sense of that whole graph in terms of the problem we just talked about. So that means deciding what quantity is on the x-axis and what quantity is being graphed on the y-axis. 30 seconds, go, figure it out. What quantity is the x-axis for this graph? What quantity is the y-axis? What's the meaning of what you're looking at? Okay, so I want to make meaning out of this graph. What does it have to do with the flag situation? What does it have to do with the flag situation? What kind of graph is that? Just first and foremost, what is that? Okay, I heard height, I heard accumulation, I heard rate of change. What is it? This is a rate of change. A representation of the rate of change. So what is on this x-axis here? Okay, and what variable do we have for that? The variable is the letter. So x, right, was the seconds since, I'll just put top so that we know, since the flag is at the top, okay? Seconds since the top. That was what we said for x, and that is truly what's on the x-axis here. So at some point, there was some experience where this flag went down. And so then it started at the top, and then time started changing, and x took on all these values of time, right? X took on all these values of time. And as that happened, what does this graph tell us? What is the y-axis? It's the rate of change in height, right? You should see that that's the rate of change in height, because what's happening to the rate of change in height as time goes by? It's constant at negative 0.75. So this is this value of negative 0.75 staying constant no matter what x is. So this is m. This is our rate of change of height with respect to time. So at 2 seconds after the flag left the top, what's the rate of change of the flag, of the height? Negative 0.75, that's that point right there. That point tells us that at 2 seconds, the rate of change is negative 0.75. At 3.4 seconds after the flag started being lowered, what's the rate of change? Negative 0.75, that's that point right there, telling us that at 3.4 seconds, the rate of change is still negative 0.75. So when you look at that line, what are you really looking at? Yeah, but what does that line consist of? What is it really? It's points, you guys, it's points. I was expecting a reaction from my previous semester, right? When you look at that graph, when you look at any graph like that, you are looking at a set of points. It's just easier to draw it this way. But what you imagine is just a zillion points. That's what you should be imagining. Given a value x, it's the corresponding, in this case, rate of change, as a point on that, and then a zillion points can be just expressed quickly by drawing a line, in this case, a line. Okay, so now we're talking about, so now I want to show you another graph here over the right. I want you to give in the flag situation, I want you to make sense of this graph. What could this graph be? What is the x value? What is the x axis quantity? What is the y-axis quantity in the flag lowering situation? Make sense of this one. Go. Okay. What is this graph over here representing, generally? Generally, what is it representing? What's that? They're still saying rate of change. Is it rate of change? Is it height of the flag? It can't possibly be height of the flag. Why not? Yeah, so the flag would be under the ground. And it would be doing some kind of weird fluctuations through the soil, right? Okay? No. Okay. So instead, we notice, look, hey, we still have this negative 0.75 happening a lot. So, some are saying this, yeah, so some are, yeah, so you've seen it. So as you're pulling, the actual pulling motion would be a constant, but then what would happen then? There'd be a pause, right, in the change in the height, and then you grab the next hand, and then again, so every time the soldier pulls down, there might be something close to negative 0.75. But in between hands, the flag is kind of stopping for a moment, slowing down, and then speeding back up to that constant rate. So what? So this is more realistic, right? So this is like rate 1. We'll call this rate 1. And it's kind of a crude model, right? A crude model, whereas rate 2 is like a more realistic model of the rate of change, okay? A more realistic model of the rate of change. So let's go back to this question of how much did the flag heights change from 0.8? So we said from 0.8 to, is that right? 0.8 to 2.4? 0.6, thank you. So starting at 0.6 seconds, that's right here, 0.6 seconds, to 2.4 seconds. Here we have this, what? This is our dx, which was 1.8 seconds. And how much did the height of the flag change in that 1.8 seconds? Negative 1.35 meters. And that was easy because all we needed to do was m times dx. So this is why we like constant rate of change, because it's an easy calculation. You just take the change in time and multiply it by that constant rate, and it just spits out that change in distance. But it's a crude model, right? It's easy, but it's a crude model that's maybe not so realistic. So let's come over here. So now we want to do the same thing for a change in time of 0.6 to 2.4. And so now, again, that total change in time is 1.8. What's the change in height of the flag? What's the change in height of the flag now? Well, what's happening to m? It's not constant. We've got a changing rate of change. And so if we have a changing rate of change, our mdx can't help us for a period of time where the rate of change is changing. It can't help us. You see that? So it's kind of like impossible. As soon as a little time goes by, the rate is different. It's like, oh, well, we don't know how much the height of the flag has come down. At a constant rate, we know that for every second, it's coming down 3/4 of a meter. So we can just say in 1.8 seconds, it's going to come down negative 1.35 meters. But here we run into difficulty. So what we want to do is we want to use that principle along with this changing rate to kind of get some kind of answer. And so what we do is, I got to go fast. This is in your homework. Let's do this. Let's split up this whole change of 1.8 into little changes of 0.3. So we're going to go from 0.6 to 0.9, from 0.9 to 1.2, 1.2 to 1.5, 1.5 to 1.8, to 2.1, to 2.5. And we're going to call each of those little changes, instead of dx, we're going to call those delta x. So delta x is 0.3 seconds. So I have 6 intervals of 0.3 seconds, and in each of those intervals, it would sure be nice to have a constant rate of change so I can use that easy math over there. So that's what I'm going to do. In this first interval, what should we say that now M1 is? For the first interval, what should we say M1 is? Certainly we can use negative 0.75 because it looks like it. So that's going to be our M1. M1 is going to be negative 0.75. And now I can use this little equation, m dx, to find out how much the flag went down in that first interval of 0.3 seconds. Now in the next one, from what? 0.9 to 1.2. I've got a severely changing rate here. But to use the easy math, I need a constant rate. So let's just give ourselves a constant rate. What constant rate would kind of fit there? We're just this is eyeballing it. So what constant rate? It's going to be definitely less than negative 0.75. So what it does? It goes from negative 7.5 up to about 0. And it hovers down here a little bit, so maybe negative 0.4. Is that a reasonable estimate for a constant rate that's kind of trying to be like the actual rate? Do you see that? So we see it's changing from negative 0.75 up to 0. So let's call it negative 0.4 the whole way. And again, now we have M2, we have a constant rate, and we can use this, our math, to figure out. So we'll say negative, or M2 is negative 0.4. Let's just do one more. So now here from 1.2 to 1.5, it starts at 0, again, ends back down here at negative 0.75. Looks like the same thing, right? So I'll just put it like that. And maybe M3 is also negative 0.4. So I'm making just rough estimates of constant rates that are trying to be like the changing rate graph. So I'm putting together a new graph of constant rates of change that's trying to mimic the real changing rate graph. And then what can I do? So then to get dy for rate 2, how am I going to get the total dy for rate 2? I can calculate the little change in the first 0.3 seconds. How do I do that? M1 times delta x. And then, so just hold on just hold on one second. You need this for your homework. Make sure you got it. Okay, and then how many of those are we going to have? Please don't pack up, because then people next to you pack up, and people next to them pack up. So just, I'll let you out early another day, okay? So M1 is? So we estimated the rate to be that in the first 0.3 seconds, and so then the little change for that 0.3 seconds will be m delta x. And then for the second, we estimated a constant rate of negative 0.4 for the time change from 0.9 to 1.2 seconds, and that was a change in time of. Okay, so then what I'll do is I'll keep estimating and using m dx on each little part to come up with an estimate, given the second rate graph, an estimate of the change in height of the flag. Is it going to be, we got negative 1.35. Is our estimate, should it be higher or lower, a bigger negative or a smaller negative than the negative 1.35? Smaller, because we've got periods of rate that's a less negative rate, right? So we're expecting something maybe more around 1, negative 1. Okay, so you have homework for Wednesday. Let me show you. On Blackboard, there's somewhere called Homework and Docs. You're going to print out, it's a 2-page handout. We're going to work through that handout. And go ahead and do your final work to turn in on that handout. Okay, and you're going to bring that, return in the first thing on Wednesday. We're going to turn that in. Go to recitation today if you have it.